Hello and welcome to ZTEC's webinar on Advanced Ultrasonic Techniques for HTHA Detection and Assessment. My name is Michael Mussman of ZTEC. I'd like to thank everyone for joining us today. As an on-demand webinar, there is no live question and answer section at the end. Instead, you can easily send us questions at any time. Simply email webinars@ztec.com and we will respond directly back to you. Before we begin the webinar, I'd like to give a quick overview of ZTEC. ZTEC is a global NDT leader. For over 50 years, we've advanced the science and standards in both ultrasonic and eddy current technologies, setting new heights in inspection performance, productivity, and predictability. ZTEC's proven expertise and complete product portfolio serve the inspection needs of our customers worldwide in transportation, power generation, manufacturing, and oil and gas. ZTEC is a subsidiary of Roper Technologies. Let's get to today's session, which will be presented by Guy Moss. Guy has been involved in advanced UT method development and implementation, capability assessment, and software development for more than 25 years. Since 2000, Guy has held various positions at ZTEC and R&D Tech, including Sales Director, Product Manager, and UT Applications Manager. Guy is currently the Sales Engineer Director UT at ZTEC. With that, I'd like to now turn this webinar over to Guy.
Thank you, Michael. Hello, I'm Guy Moss, and I have the pleasure of presenting this webinar on advanced ultrasonic techniques for HTHA detection and assessment. This is our agenda for today. First of all, I will give an introduction on HTHA and on the specific NDT inspection challenges related to this damage mechanism. After that, I will give a short overview of legacy inspection techniques for HTHA as indicated in previous editions of the API Recommended Practice 941. Then I will introduce the key elements of the recommended global inspection solution for HTHA. We will take a deeper dive into the principles of the proposed advanced ultrasonic techniques and look at the results they provide on samples with confirmed HTHA damage. After that, I will show how optimization of the phased array probe design can potentially improve the quality of inspection results on HTHA and other challenging defect types. I will also talk briefly about the Topaz 64, ZTEC's versatile, high-performance phased array system that supports all the previously discussed advanced UT methods. And finally, we will wrap up with some conclusions from the presented material. So let us first look into the damage mechanism. High-temperature hydrogen attack, or HTHA, occurs in low-alloy carbon steels operating at high temperature, typically above 205 degrees Celsius or 400 degrees Fahrenheit. It occurs in hydrogen environments that are typically present in refineries, petrochemical plants, and chemical facilities. Under certain conditions, hydrogen atoms will diffuse through the exposed steel, and within the metal, the hydrogen will react with carbides to form methane gas. The methane molecules are larger than the hydrogen atoms and therefore cannot diffuse through the steel. The methane accumulates in voids at grain boundaries, and this eventually leads to fissures and cracking. HTHA has a number of critical factors. Obviously, temperature, hydrogen partial pressure, and time are important parameters, but also the stress level at a particular location in the component. Typically, the heat-affected zone of welds and structural discontinuities in vessels are suspect locations. Obviously, ultrasonic techniques will have to be adapted to allow for inspecting these specific locations. The API Recommended Practice 941 defines 4 stages in the lifetime of steels experiencing HTHA. Stage 1 is called the incubation period. During this period, methane voids appear around grain boundaries. The voids are very small, typically less than 1/100th of a millimeter or 4/10,000ths of an inch, which is at least an order of magnitude smaller than commonly used ultrasonic wavelengths. Therefore, we must consider that this level of damage is currently beyond the detection capability of ultrasonic testing. Stage 2 damage is characterized by fissures along the grain boundaries, and the mechanical properties of the metal begin to degrade. In stage 3, the fissures align and grow into micro-cracking, while the mechanical properties are rapidly deteriorating. And finally, by stage 4, the component is at significant risk of failure by cracking. So at this time, the challenge for NDT is to detect the damage in operating components as it moves into stage 2, because in the later stages, the risk of failure is dramatically increasing. Unfortunately, such a dramatic incident happened in April 2010 at the Tesoro Anacortes refinery in the state of Washington in the US, when HTHA damage led to a violent rupture of a heat exchanger, causing catastrophic fire. So inspection for HTHA is obviously a necessity for this industry. Let us first have a look at methodologies that have been in place for a while. The API Recommended Practice 941 suggests potential inspection techniques for HTHA based on available published information. It provides a short description of the techniques and lists advantages, disadvantages, and the area of application. This slide shows a short list of the legacy techniques deployed in the field, mostly by manual scanning. Various physical principles are used. Most of the techniques have a good theoretical basis and are in some cases supported by empirical evidence. However, a joint industry project in the US, started in 2012, has recently reported on the experimental assessment of a number of those techniques. The study was ran as a round-robin trial with metallographic evaluation to verify the results of the UT techniques as deployed by several NDT service vendors. The results of the round-robin trial showed a significant number of both false positive and false negative calls for individual legacy techniques. There are a number of possible causes for the poor performance of the legacy techniques. First of all, in general, they are difficult to implement practically, and the surface condition of the components can strongly influence their effectiveness and reliability. And second, at least half of them are not suited for using on welds and heat-affected regions. So clearly, reliable detection and assessment of a challenging damage mechanism like HTHA calls for a different approach. Industry experts now believe that the solution lies in developing and deploying an efficient and robust inspection strategy combining multiple advanced ultrasonic examination techniques for initial screening of material and for further assessment of suspected locations. There are significant benefits for using encoded scanning techniques, especially when the quality of the recorded data is verified during the inspection. Encoded scanning reduces the probability for missing certain areas of the component. Also, the archived data can be used for future review and comparison with new data from similar or other inspection techniques as the component ages. Given the expertise required to evaluate the weak signals and the patterns generated by HTHA, it is of great importance that operators successfully attend damage-specific training courses on specimens with confirmed HTHA. For instance, the course regularly offered by Lavender International. This is also a good time to thank Tim Armit at Lavender for letting us use the images that we recorded on various of his HTHA specimens. The use of carefully selected UT and phase array probes is important in order to optimize the performance of the applied examination techniques. And finally, Efficient deployment of this inspection strategy requires a powerful portable phase array unit like ZTEC's Topaz 64, with all the tools and features to set up and execute the recommended examination techniques that we will discuss in the upcoming slides: TUFT, TULA, beamforming phase array, and live TFM. Let us kick off with TUFT. The time-of-flight diffraction technique has been successfully used for more than 2 decades for the inspection of a wide range of carbon steel welds. The technique is very effective for the detection, characterization, and sizing of embedded flaws, and also for accurate through-wall sizing of far surface cracks. In recent years, it was confirmed that TUFT is also a rapid and robust technique for initial HTHA damage screening of base material and the heat-affected zone of welded regions. The presence of increased grain noise in the form of short indications and clustering in the TUFT A-scan signals are indicative for early-stage HTHA. The use of high-quality TUFT probes with piezo-composite active elements is strongly recommended. The probe size and the frequency depend on material type and wall thickness. For thinner components, typically an inch thick, 10 MHz diameter 3 mm probes are very suitable. And clearly, the same TUFT technique will also be effective to detect and size HTHA-induced macro cracks. My next slides will show images generated with the TUFT technique on several types of HTHA damage in field-removed specimens. My first image shows 10 MHz TUFT data from a longitudinal vessel weld with severe HTHA damage in the heat-affected zone. The typical HTHA signature can be observed: a multitude of short grain noise indications in the B-scan and clustering in A-scan signals. The next example shows data from the same TUFT technique on a skid bar attachment weld located at the ID of a vessel. In this case, we are looking at a typical macroscopic ID crack induced by HTHA located at the skid bar attachment. And my last TUFT slide shows data from the same skid bar attachment weld, this time while scanning the TUFT perpendicular to the skid bar weld. Using this TUFT configuration, we can clearly see that there are actually 2 ID cracks, one on either side of the attachment. For components with a wall thickness over 50 millimeters or 2 inches, the TUFT technique becomes less effective because of the combination of beam divergence and long sound path. The TULA or TUFT ultra-low angle probe design offers an alternative for these thicker components. The design integrates the transmitter and receiver elements on separate wedges in a single probe casing. The TULA probes basically act like 0-degree transmit-receive probes and are available with specific focal depths, allowing to optimize detection throughout a range of thicknesses. The acoustic beam simulation for one of the commercially available TULA probes is shown on the right side of my slide. As for the TUFT technique, the presence of increased backscattered noise and clustering in the A-scan and recorded B-scan signals are indicative for early-stage HTHA. My slide shows the data recorded with the TULA probe on a thick specimen with severe HTHA damage. The introduction and adoption of portable phase array units has been a leap ahead for ultrasonic inspections of critical components in various industries. Phase array UT is a mature and industrially accepted technique for volumetric inspection of components and welds since more than a decade. Phase array provides an image of the inspected region in addition to the traditional A-scans, and therefore allows for a more intuitive interpretation of the results. The technique allows to rapidly cover the complete examination volume by combining sectorial scanning or electronic linear scanning with a mechanical movement. Also, it provides a permanent data record for offline review and comparison with previous results. Two commonly used phased array techniques are also useful for detection and assessment of HTHA damage. For examination of the heat-affected zone under a weld cap, a 1D linear array probe on a shear wave wedge allows to cover the region of interest with a sectorial scan. The typical configuration is illustrated here. As we can see on the animation in the UltraVision software, direct insonification with high-angle beams is combined with skipping low-angle beams of the ID surface. Typically, 5 Megahertz probes are used to generate shear wave beams from 35 to 75 degrees. For examination of base material, or if the weld crown is ground flush, a 1D linear array probe in direct contact or fixed on a 0-degree L-wave wedge can provide good coverage using electronic linear scanning with a partial aperture of the probe. This animation illustrates the probe configuration and the coverage of the straight beam examination. For this case, 10 MHz probes will typically be used. Comparison of the responses from the shear wave beams and the L-wave beams can help to discriminate between HTHA damage and inclusions in the base material. My first example for the phased array technique shows data from a longitudinal weld, almost 1 inch thick and with severe HTHA damage in the heat-affected zone. In this case, a standard 5 MHz 64 element probe was used, but the active aperture included only the 32 elements closest to the weld. This is exactly the configuration I just showed on the animation. Using a partial aperture of the large probe brings the beam exit point closer to the weld and increases the direct coverage. Also, the smaller active aperture provides more depth of field, which is more appropriate for detection scanning. First of all, we can observe a relatively high noise level on the data, higher than what we're used to see on data from generic weld inspections after manufacturing. As mentioned before, early-stage HTHA damage generates pretty weak ultrasonic responses, so the recommended sensitivity settings for HTHA detection will be at least 12 dB higher than for generic inspections. Obviously, this also results in a higher average ultrasonic noise level on the data. The indications from the HTHA damage can be clearly seen in the near side heat-affected zone close to the ID surface. And this is the image from the same weld, examined from the other side. We can see similar indications in the heat-affected zone on the other side of the weld, but at a lower amplitude. My next slide illustrates the straight beam phase array technique using a 10 MHz probe in direct contact with the component. Unfortunately, the weld crown was not ground in this case, so the probe could not be positioned close enough to the weld to insonify the HTHA damage in the heat-affected zone. The examined region covered by these data is purely base material, and the observed indications are most probably inclusions. The most recent progress in ultrasonic phase array examination involves full matrix capture and advanced focusing techniques. With the full matrix capture or FMC technique, the elementary A-scan signals from every transmitter-receiver pair in the phase array probe are captured and recorded. In the new generation of high-end phase array units, it is possible to process these elementary A-scan signals live during the inspection and generate UT images with advanced focusing techniques. The most commonly used advanced focusing algorithm is the total focusing method, or TFM. This animation explains how it works. The algorithm sums the elementary A-scans from all elements in the array to generate a frame of pixels, where each pixel is computed using a dedicated focal law. The TFM frames can be used for live interpretation, or they can be stored for each position of the probe, very similar to a dynamic merge view in regular phased array. The process results in nearly ideal focusing in each point of the image, and this improved image resolution can allow for better characterization and sizing of challenging damage mechanisms like HTHA. The elementary A scans from the FMC data recording can also be used with another advanced processing method to generate a sectorial sweep of A scans while focusing in each point along the sound path. We will call this technique sectorial total focusing. Its physical principle is very similar to the well-known DDF or dynamic depth focusing algorithm, but this time applied both in transmission and in reception. Again, the operator can perform online data interpretation, or the images can be recorded during an encoded inspection sequence. The algorithm has the benefit of recording a summed A-scan signal for each angle, very similar to standard phased array UT, which may be more intuitive for the experienced phased array technician and facilitate the acceptance in codes and standards. My next example illustrates the use of the TFM technique. The considered specimen is a thick flange and contains important HTHA damage at a depth of roughly 3 inches. A 10 MHz linear array probe was used to generate L waves in direct contact with the metal. The image shows the recorded live TFM data with frames of 512 by 512 pixels. On this thick component, high-resolution frames are required to satisfy the recommended amplitude fidelity criterion of 2 dB for TFM examinations. At the right side of the recorded data, we can see the virtual acoustic beam that represents the strong focusing capability and excellent lateral resolution of the applied TFM algorithm. We can observe that the high-frequency probe, in combination with TFM, allows to detect and visualize typical HTHA damage. Industry experts consider that the excellent focusing capability of TFM is an important asset for better characterization of HTHA damage. As a provider of complete inspection solutions, ZTEC's goal is to optimize the various components of the considered solution. So let me address some probe design considerations to further improve the inspection capability for HTHA. The generic phased array probes we saw earlier have proven their effectiveness for the detection of welding defects, but when searching for small flaws with weak ultrasonic responses, optimization of probe and wedge parameters can mitigate some of the drawbacks and limitation of these generic probes and provide additional benefit for HTHA assessment. For shear wave inspection of the heat-affected zone in welded components with wall thickness around 1 inch, ZTEC designed the TFM AL5 Megahertz Probe. It has 64 elements and a very small pitch for improved steering with beamforming phased array and improved TFM imaging. Also, the active element is curved in the passive direction for better focusing and improved lateral resolution. As shown on the acoustic beam simulation, this results in a focal spot size as small as 1 by 1 millimeter, and therefore an important increase of the acoustic energy concentrated on small flaws and a better signal-to-noise ratio. The TFM AL design combines optimized aperture and reduced wedge footprint compared to the generic 5 MHz probes, and this gives better access to the heat-affected zone and the weld region. To facilitate setup of this new probe type, the probe and wedge parameters can be easily imported from the database in the UltraVision Touch software. Variations of this probe design are also available for components with different wall thickness. This slide compares phased array examination data from our new TFM AL5 MHz probe with data from the generic LM5 MHz probe. In both cases, the appropriate 55-degree shear wave wedge is used. The specimen is a circumferential weld of roughly 1 inch thick and contains HTHA damage along the heat-affected zone on the right side of the weld. We can see that both probes allow to detect the damage, but the strongly focused beam of the new TFM AL design provides a better signal-to-noise ratio and detects more HTHA clusters and micro fissures. As a result, we can expect a more accurate global assessment of the damage. ZTEC also proposes a new probe design for L-wave inspection on components with wall thickness around 1 inch. The TFM DLA 10 Megahertz probe is an integrated dual linear array probe designed for pitch and catch inspection. Both transmitter and receiver have 64 elements and a very small pitch for improved TFM imaging. Again, the objective of the design is to obtain better focusing and improved lateral resolution in the passive direction. But in this case, the autofocusing behavior of the transmit-receive configuration is used to meet the objective. The acoustic beam simulation shows a focal spot size of 1 by 2 millimeters. We will see that this leads to better imaging and a better signal-to-noise ratio on HTHA damage and other flaws compared to the generic pulse echo probe design. Of course, the parameters of this new probe are also available in the UltraVision Touch database. This slide compares live TFM examination data from the new TFM DLA 10 MHz probe and our generic LM10 linear array in direct contact. We are essentially looking at base material here, so the indications are most probably inclusions. Still, we can clearly see the benefits of the DLA probe design. First of all, this design eliminates the strong interface echo that can mask important indications when using the generic pulse echo probe design. Second, the excellent signal-to-noise ratio of the DLA probe allows to detect more and smaller indications. And finally, the better lateral resolution in the passive plane improves the imaging capability of these small indications. And these are examination data from the new TFM DLA probe on a skid bar attachment weld. We can see a clear linear indication from a macroscopic ID crack, but also clusters of HTHA damage higher up in the material. Let us now talk about the last keystone of the inspection solution, ZTEC's most versatile and high-performance phase array unit, the Topaz 64. The Topaz 64 has a 64-128 PR phase array configuration that allows for two-side inspection of thick welds with a 64-element active aperture. It also has two separate conventional TUFT channels at 200 volts, well suited for the initial screening of components for HTHA. In addition, the Topaz 64 also offers best-in-class live high-resolution TFM and STF. The Topaz 64 allows to perform encoded scans, motorized or manually driven, and record live TFM frames or STF channels in parallel with one or more standard phase array channels. This allows to speed up the global inspection process. After the recording, the TFM is available as an actual merged data group in UltraVision Touch, and the STF data can be exploited like a standard phase array UT sector scan. In addition to the typical negative square pulse, 75 volts on 50 ohms, the system can also generate a bipolar pulse of 150 volts peak to peak on 50 ohms, which generates 40% more acoustic energy. This contributes to the overall signal-to-noise ratio of the ultrasonic signals, which is particularly useful when recording the very weak flaw responses which are typical for HTHA. Like the other Topaz units, the Topaz 64 is controlled by the industry-proven embedded UltraVision Touch software. Based on the information presented in our webinar, we can draw the following conclusions. Although progress has been made in recent years, HTHA damage remains a challenge for early-stage detection and reliable assessment with ultrasonic inspection techniques. The key for success is an efficient and robust inspection strategy executed by adequately trained operators. This inspection strategy should combine multiple advanced techniques: TUFT, TULA, beamforming phase array, and live TFM. Carefully selected UT and phase array probes are paramount to optimize the inspection performance. And a versatile and high-performance phase array UT system like the Topaz 64 is required to efficiently set up and deploy all examination techniques recommended by industry experts and leading training schools. This concludes the presentation part of our webinar. I will now turn it back over to Michael for a summary.
On behalf of everyone at ZTech, thank you again for attending this webinar. If you are interested in learning more about our solution or have additional questions, please email us at webinars@ztech.com. To learn more about ZTech, visit our website or follow us on social media. This concludes our webinar. Thank you and have a great day.